Hi there, and welcome to today's webinar, sponsored by Inside GNSS, Inside Unmanned Systems, and Mcor Corporation, and hosted by WebAttract. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. In just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they address the technical breakthroughs in inertial technology that have created new possibilities for gyroscopes and inertial measurement units and new frontiers that have opened up for targeting, autonomous navigation, ISR, and more. We've invited you along with over 260 professionals from 33 countries representing a variety of industries. And over the next 90 minutes, regardless of your industry segment or your location, we're confident you'll find today's webinar of value. Now, before we get started, Richard Fisher, publisher at Inside GNSS, Inside Unmanned Systems, would like to take a moment to welcome you and introduce our sponsor, as well as our main moderator for today's session. Over to you, Richard.
Thank you, Lori. I appreciate that. On behalf of Inside GNSS, Inside Unmanned Systems, and today's sponsor, the Emcore Corporation, I extend a warm welcome to our audience from around the world for today's webinar. We're delighted you're with us today. And I'd like to introduce our moderator for today's webinar. Alan Cameron is our editor-in-chief of Inside GNSS magazine and the PNT editor for Inside Unmanned Systems. He's covered the GNSS, PNT, and autonomous industries as a writer, editor, and thought leader since 2000, focusing on technical issues around continuous, reliable positioning and navigation. Alan, the floor is yours. Welcome.
Thank you, Richard. Thank you, Lori. And thank you to everyone around the world who's joined us today for this webinar. It's going to be an exciting one. I have personally learned quite a bit about advances in inertial technology as we have done the run-up, the preparation for this webinar. So you have a great show in store for you. Briefly looking at our panel, from the company From Mcor, we have a vice president, we have a chief scientist, we have the director of fiber optic gyroscope research and development, and we have the director of sales and marketing. We'll hear from each one of these gentlemen in turn. First, Lori, we've learned a little bit about the composition of our audience. Let's learn a little bit about the predilections of our audience.
Absolutely. And folks, coming up on the screen is our first poll for today. In general, what are the most important performance characteristics of an IMU or INS? And today we are asking on the honor system if you would select your top two of these choices: a gyro-based in-run stability, startup time, low gyro noise, low accel noise, shock, and vibration resistance. So again, we're looking for your top two. Okay, looks like we have 76% coming in with gyro-based in-run stability, 10% startup time, 51% low gyro noise, 21% low accel noise, and 42% shock and vibration resistance. Alan?
Well, since we've asked the audience to select two, it's hard to pick a clear leader because people are voting 1 and 2, but certainly gyro-biased in-run stability has the most combined votes. Low gyro noise and shock and vibration resistance coming in following. I'm going to throw this over to the Emcore panelists to see what conclusions they might draw about the audience and their performance characteristic preferences. Gentlemen?
This is David Hoy here. It's not surprising, particularly when you're looking at navigation flight control for autonomous systems or platforms, where in-run bias stability is needed over, a shock and vibe resistant environment. So that combined with low noise gyros for non-line of sight targeting, pointing, instability seems to be ideally suited for those applications too. So this is what we hear from customers time to time as we go out and work with them. So it sounds like we have the right customer set today.
Terrific. First, I'm going to turn the floor over to Dave Wojciechowski, Vice President at Emcore, to give us a little bit of setup as to the company and the content of the what we're going to be hearing. David?
Thank you very much. And for everybody on the call, many thanks for your time today and for joining Emcore's webinar on resetting the bar on inertial sensor size, weight, and performance for tactical and navigation applications. As mentioned, my name is Dave Wojciechowski. I'm Vice President of Sales, Marketing, and Business Development here on the aerospace and defense side of the business. You know, I got a couple of slides here. Emcore has been transforming the inertial navigation for decades with our highest performing and highest reliability quartz MEMS and fiber optic gyro technology. Today, the team will dive deep into the foundations of the technologies and highlight our latest products that showcase our best-in-class performance. Emcore's products are used today in a wide range of applications, from optical targeting systems, oil and gas, to weapons and north-finding and true navigation systems. Our products are rigorously tested and application qualified to provide the user with the confidence in the accuracy of the system today and tomorrow. Our aim, Emcore's aims, to be a technology disruptor in inertial sensors and measurement units by continuing development of gyroscope, accelerometers, and inertial navigation systems, which provides our customers with higher precision, compact form factor, and ease of use. Looking at the system performance range needed in the market, there is the industrial grade at 10 to 100 degree per hour, tactical grade at 5 degree to 0.3 degree per hour, high-end tactical and mid-term navigation grade at 0.3 degree to 0.01 degree per hour. Emcore sensors have you covered over a broad range of this performance. As a side note, Emcore is one of the few companies in the world that have product offerings spanning such a wide range of performance. A major highlight is that Emcore is vertically integrated, and a lot of folks say, well, what does that mean? All of the major active components within our FOG and quartz MEMS products are manufactured within Emcore. These are not outsourced. This gives us a greater ability to control our manufacturing processes and providing the highest level of quality to our customers. What's shown here is our current product portfolio, showing our broad range of sensors, IMUs, and navigation systems. Our portfolio is constructed with both fiber optic gyros and quartz MEMS gyros accelerometers. Depending upon your specific application, we can recommend a solution which will meet your requirements. Today, we will look at two applications, one for the quartz MEMS and one which covers our fiber optic gyro technology. I will now turn this over to our technical experts to dive deep into the details. After the webinar, feel free to contact our technical marketing team regarding your specific application need. Their contact info will be shown at the end of the presentation. And again, we really do appreciate your time today. Back to you, Alan.
Thanks, David. As David mentioned, we're going to be diving deep into two inertial technologies, each of which is ideally suited to particular end-use applications. And in the first instance, that of gyro compassing and north finding, this involves quartz MEMS. And to learn more about quartz MEMS, we're going to hear from Sergey Zotov, Chief Scientist at Emcore, with principal responsibility for the development of quartz MEMS, advanced micro-machined inertial navigation sensors and systems. From 2014 to 2018, Sergey was a senior engineer with General Electric Global Research, where he formed and served as the principal investigator of 3 DoD-sponsored projects. Over the last 19 years, his focus has been on the research and development of MEMS gyroscopes and accelerometers. He's authored more than 50 peer-reviewed journal articles and international conference papers in inertial MEMS navigation, and he holds 10 U.S. patents. He received his master's and PhD degrees in mechanical engineering and control systems from Tula State University in Russia in 1999 and 2002. And from 2008 to 2014, he was a postdoctoral scientist with the Microsystems Laboratory at the University of California, Irvine, in the U.S. Sergey, please give us your presentation on tactical to navigation grade quartz MEMS-based IMUs.
Alan, thank you for introduction, and hello everybody. I'm Sergey Zotov, Chief Scientist of Emcore, and today I will provide you some detail about our tactical grade IMU, high-end tactical grade IMU, and navigation grade IMU based of quartz MEMS devices. Today we will learn why we use quartz, not silicon. How does quartz MEMS work? I will provide you some evidence that we already built high-end tactical grade gyroscopes, high-end tactical grade accelerometers, and IMU based on these devices, and show you some experimental results on our navigation grade accelerometers and future navigation grade systems. We know during last several years Mcor has leadership in tactical grade market. When we say tactical grade, we mean truly tactical grade, when we achieve 1 degree per hour for gyroscope over environment and 1 millig for accelerometer over environment. We provide you gyroscopes, single axis, IMU based off quartz gyroscopes and quartz accelerometers, and INAs based off quartz inertial sensors. All our devices are MEMS, and usually when we say MEMS, it's associated with silicon. But we use different material. We use crystal quartz. And why we to build our gyroscopes and to build our accelerometers. And why we use crystal quartz? This material was selected because of its property. I would like to provide a little bit more detail why this crystal quartz property is so unique for inertial MEMS. First of all, quartz has strong piezo effect. And we're using this piezo effect to excite quartz resonators. Technically, you cannot excite silicon. For silicon, you need to build some additional structure. Since we use our piezo effect for quartz, we're able to excite our devices with much larger amplitude. And it's improved our angular random walk and velocity random walk, which is white noise for gyroscopes and accelerometer, by factor maybe about 100 compared to the same footprint of silicon devices. The other important parameter is stability over time. We know that quartz was standard for time standard before atomic clock. And also we know that all navigation grade or high tactical grade devices utilize calibration and self-calibration algorithm to achieve high performance. And if you calibrate your device in the lab and turn your device in 10 years after calibration, your device is supposed to have the same parameters to calibrate everything back. If your parameters of your device deviate over time, it will be pretty hard to calibrate everything to high-end tactical grade performance. So stability over time, it's very important parameter of the quartz. The third important parameter is temperature coefficient of frequency, which means how frequency change over temperature due to Young model change over temperature. Why it's important? Because we use frequency modulation accelerometer where our output is frequency. And if our frequency deviate over temperature, it means our signal deviate. Of course, we're able to calibrate the deviation over temperature, but it will be much easier to calibrate if this deviation very little. For example, quartz temperature coefficient of frequency, it's about 50 part per million over military temperature range. When I say military temperature range, I mean negative 55 degrees C up to 90 degrees C. At the same time, for silicon, this number is about several thousand part per million over this military temperature range. And also, this temperature coefficient of frequency is important for gyroscope as well, because frequency change proportionally scale factor and frequency change. This is the reason why our bias deviate. So stability of frequency coefficient is important for us as well. In future, I'll show you how these parameters allowed us to achieve high tactical grade gyroscopes and accelerometers. Let me explain how our quartz MEMS gyroscope does work. We have tuning fork drive tines. When we excite these drive tines in plane out of phase. When we feel rotation, these drive tines oscillate in out of plane anti-phase. And this mechanical oscillation, mechanical coupled with pickup tines. So due to rotation, amplitude of pickup tines proportional to this angle rotation. We pick up this amplitude of pickup times, and output voltage of our gyroscope will be proportional of our input rate. When we discuss about MEMS gyroscope, we usually think it's low performance and low cost, but it's not always low performance. Let us understand what is fundamental limit of gyroscope performance. We use Coriolis vibratory gyroscope, and there is some fundamental limit for this Coriolis vibratory gyroscope performance from mechanical thermal noise or from Boltzmann noise. White noise of the gyroscope inverse proportional to amplitude of gyroscope. And if we use silicon gyroscope, since you cannot excite silicon itself, you have to build additional structure for gyroscope structure excitation, like capacitor. And you excite the silicon structure through this capacitor. And this very limited your amplitude of excitation. Usually this gap is about 1 micron or less. And amplitude of excitation for silicon is a fraction of micron. At the same time, we are able to excite our quartz itself. And our amplitude of excitation for standard devices is about 20 microns. Sometimes we achieve 40 microns, which is at least 2 orders of magnitude larger than silicon. Since angular random walk inverse proportional to amplitude of excitation, for the same proof mass footprint, for the same frequency, we can achieve at least 2 orders of magnitude low white noise for our gyroscopes. The other important parameter for gyroscopes is proof mass. Our white noise inverse proportional to square root of proof mass. But again, for silicon, it will be pretty hard to age silicon deeper than 100 micron. For quartz, we achieve these parameters about 1000 microns, which is about 10 times deeper than silicon. Again, it's help us to improve our angular random walk or white noise. So we know that fundamental limit of our quartz gyroscope pretty low. What about practical? In practice, in our facility, we develop a number of gyroscopes, and we able to achieve angular random walk of this gyroscope about navigation grade or slightly better. Our angular random walk, it's about 0.8 millidegree per square root of hour. For some experimental gyroscope, it's about half millidegree per square root of hour, or maybe 1 millidegree per square root of hour. And it's interesting, this is limit, this is a performance, it's not limited by quartz structure. It's still limited by electronics. We still have some gap and we're potentially able to achieve strategic grade white noise for gyroscope if our customer asks us to do this. But right now, we park on navigation grade white noise. Why? Because this performance of the gyroscope is already good enough to build a gyro compass. Of course, gyroscope has a lot of other parameters like scale factor and bias, but even for just a moment, we focus on angular random walk only. This device is already good enough for gyro compass. Let me show you some gyro compass experiment. Here at Emcore facility, we're able to demonstrate gyro compass based off our gyroscope with accuracy about 1 milliradian after 100 seconds. We sent our devices to a few our potential customers, and they confirm that our performance of gyro compass built from our gyroscope, it's about 1 millidegree after 100 seconds. But angle random walk of gyroscope provide your fundamental limit for gyro compass. And if you have ideal Kalman filter, and if you cruise-sail this east-west direction, you are able to achieve number much better than what we demonstrate you. Why it's happened? It's just because we were limited not of gyroscope white noise. Our system was limited by rotary stage noise. For example, if you do experiment in isolation foundation, it's ideal arithmetic or cutronic rate table in very quiet environment. Ideally, you can achieve this fundamental limit. But in reality, when you go to outside with your gyro compass, you will be limited by white noise, not gyroscope white noise, but your platform. And what we observe here. From this slide, we can guarantee you that if you build gyro compass from our gyroscope, you will never see noise from our gyroscope. You will always limited by noise of your platform, I mean in real environment. We developed gyroscopes for gyroscope compass more than 10 years, and we provide these devices for our customers. These devices operate in under the ground for drill application. And all this gyroscope, we already sold about 1,200 gyroscope for underground navigation. And all this gyroscope operate in harsh environment with very hard vibration and shock plus high temperature. Temperature usually 150 degrees C. And all of our units still able to operate and provide north direction. The other important parameter for gyroscope is bias over temperature. When we discuss about a high-end tactical grade gyroscope, our goal to achieve is about 0.1 degree per hour over military temperature. Again, by military temperature, I mean negative 55 plus 90 degrees C. We built 3 IMUs based off our gyroscope, implement and all this gyroscope has very low noise, navigation grade noise. Implement our conventional calibration technique and able to achieve about 0.1 degree per hour for almost for all these 9 gyroscopes. So we are almost high-end tactical grade, but we still have some room to improve our calibration algorithm and achieve this number even better than 0.1. So since we built a number of IMU units with high navigation grade noise performance and high-end tactical grade bias, we send these units to our potential customers. This result from our potential customer, it's they are independent expert, and all this result was achieved in their facility. First of all, they confirm that we have navigation grade angle random walk, which is about 1 millidegree per square root of hour. The other important parameter, like since it's high-end tactical grade gyroscope, we have very stable in-run bias. And since you turn on gyroscope, the gyroscope, as you can see, immediately start to see Earth projection on each axis of sensitivity. For this particular unit, you're able to measure Earth rate with 1% accuracy after a few seconds before cruising. And it means you're able to measure Earth direction better than 1 degree before any cruising. Why it's important? All gyro compass use rotary stage and cruising, but to find optimal solution for north founder, you have to cruise-sail your gyroscope east-west direction. Since from the turn, if you don't know east-west direction, usually conventional gyro compass, you have to crucial it at least twice to find east-west direction approximately, which takes about 30 seconds. And only after that, your algorithm starts to operate optimal. For our gyroscope, you can save this 30 or 40 seconds. And since you can find east-west direction from the start and start to crucial east-west direction after maybe couple seconds when you estimate when you measure the direction. So it doesn't improve performance, but it's performance of gyro compass. It's angle random walk only, which is navigation grade. But the bias in tactical grade bias help us to save time to find best performance for gyro compass. The other important parameter for gyroscope is scale factor. And again, our independent customer repeat this experiment for scale factor for X, Y, and Z gyroscope 6 times. And they they show that this scale factor is pretty stable from run to run. We met about better than 30 ppm at 2 sigma bow tie for scale factor stability. But if you look at this data, we can see it's not a scale factor limited by scale factor and stability. It's limited by our bias in run bias and stability. And if we're able to improve in run bias and stability, for example, this number is 50 millidegree per hour. If we improve our in-run bias and stability, we can significantly improve bias scale factor stability. So this is all about gyroscope, and I would like slightly conclude gyroscope data. First of all, we're able to achieve navigation grade angle random walk for gyroscope, and we demonstrate that this gyroscope is suitable for North Founder. We achieve high-end tactical grade performance for bias, and we confirm that our scale factor is pretty repeatable. Next, it's our quartz MEMS accelerometer. We use frequency modulation, dynamically balanced differential principle of operation of accelerometer. This accelerometer comprises of 2 sensors, sensor 1 and sensor 2. Sensor 1 and sensor 2 has 2 beams. We excite these beams in antiphase in plane and keep tracking of frequency of oscillation of each of this beam. When we apply acceleration about X of sensitivity, resonance frequency of one beam increases and resonance frequency for the second beams decreases. We measure delta F between this F1 and F2, and this is delta F is information of acceleration. I already mentioned that quartz is pretty stable, frequency of quartz is pretty stable over temperature, at least 2 orders of magnitude more stable than silicon. But still, we have some frequency dependence over temperature. And just this differential principle of operation allowed us to calibrate over common or reject common mode errors like frequency, like temperature, because if we increase temperature, both frequency increases together, or maybe cross-axis sensitivity. So this principle of operation provides us a robust accelerometer over environment. Very recently, we implemented new type of calibration for our accelerometer and calibrate scale factor and bias of accelerometer over military temperature from negative 55 degrees C up to 90 degrees C. For scale factor, after this calibration, we observe our RMS of scale factor better than 30 ppm over all this temperature. And it's not limited, it's not our limit, because you see this hysteresis. We still have room to improve this number, and we're working on that. But this number is already a pretty low number. It's at least 10 times better than our current product. At the same time, calibration algorithm for bias reveals that we achieve better than high-end tactical grade accelerometer for bias. High-end tactical grade is about 0.1 milli G, but we achieve better than 100 micro G over temperature. Next, we observe that this bias, it's not limited by our calibration algorithm. It's just limited by our white noise of accelerometer or velocity random walk. Next, we take our course like itself and change all our electronics and change principle of operation of this accelerometer. Rebuild everything around our quartz from the scratch, and we're able to drop velocity random walk of our accelerometer by a factor of more than 100. Right now we have accelerometer that has two modes of operation, and it's operating both modes simultaneously. And for first mode, we have velocity random walk about 0.3 micro G per square root of hertz, with bias instability 0.5 micro G. But this mode has 10 Hz bandwidth only. We use this mode for calibration accelerometer over temperature. The other mode has velocity random walk half of micro G per square root of hertz, with bias instability 0.3 micro G and bandwidth 300 Hz or wider. We use this mode to measure acceleration. Next, when we drop this velocity random walk to this level, it's much better than navigation grade level. I would say high-end or strategic grade noise level for this accelerometer. When we drop this velocity random walk to this low level, we implement our calibration algorithm again. And right now, we achieve navigation grade accelerometer over military temperature. Our bias drift was better than 25 micro G, but I remind you, navigation grade means 25 micro G or low for bias overall. So technically, we have high-end tactical grade gyroscope, and we built a high-end tactical grade accelerometer to work with this gyroscope. Also, we achieve much better than navigation grade white noise for accelerometer, and we demonstrate you navigation grade performance for accelerometer with improved algorithm. This slide concludes my discussion, and I would like to remind you that during the last years, we have truly tactical grade IMU on the market with gyroscope bias 1 degree per hour over environment and 1 milli-G accelerometer bias over environment. This unit 19 cubic inches. When Mcor sponsored us to improve performance of gyroscopes and accelerometers during the last year, we able to demonstrate you gyroscope with in order to 0.1 degree per hour and accelerometer built with this IMU better than 0.1 milli-G over temperature. Our angle random walk of this gyroscope is navigation grade, and angle random walk of this velocity random walk of this accelerometer is way better than navigation grade. In parallel, right now, we start to work to squeeze size of this gyroscope, and our future product will be 9 cubic inch IMU with high-end tactical grade performance. In parallel, we figure out that it's not hard to us to achieve navigation grade accelerometer, and we already demonstrated you navigation grade accelerometer with high-end navigation grade noise. Know that we already have navigation grade fog gyroscope. We are planning to build navigation grade IMU which based on MEMS accelerometer and fog gyroscopes. Okay, back to you, Alan.
Thank you, Sergey, for that deep dive. It's accurate to characterize it as that very deep dive into inertial technology. We've had a couple of questions come in for you during your talk. One from somebody who has an application for a gimbal mount camera on a UAV and wants to know the applicability of whatever type of inertial technology you can provide for this in particular.
Yes, if you want to fuse our device with some external information, including camera for UAV, and if you always have a visual field to observe, you have only one parameter of interest. It's angle random walk. And you can completely ignore your bias, scale factor, and everything else, because your camera and external information, if you mix it, it's very tight in by using Kalman filter or any other filter, because you're able to calibrate everything else. And you have only one parameter of interest. It's good angle random walk. Because of that, I would recommend you to use our quartz gyroscope, since it's already provide very good angle random walk, and it's pretty small.
Thank you. Another question. Attendee understands that Quartz MEMS offers great performance. Can you provide more specifics about the performance of Quartz MEMS?
Yes, everything, we have some fundamental limit, and when you build and design MEMS, you need to understand where is your fundamental limit. Everything else, you can calibrate it out. And for MEMS performance, fundamental limit is, I would say it's strategic grade, or like way better than navigation grade, but it will be hard to achieve this. Right now, what we achieve in Quartz, it's a high-end tactical grade for gyroscope. I mean high-end tactical grade gyroscope for overall, and we're planning to achieve navigation grade. And for accelerometer, we already demonstrate you navigation grade performance over temperature, and we're planning to even improve this performance for accelerometer. So actually, Quartz MEMS has a very good potential and for future, and we like maybe during several years ago we didn't really pay attention on that, but right now our plan to put on the market high-end tactical grade small IMU, high-end tactical grade gyroscope and accelerometer, and navigation, maybe in future navigation grade IMU based off Quartz MEMS.
Thanks again, Sergey. We'll have more questions for Sergey and for the other two gentlemen you see on your screen here, David Hoy and David Blumenfeld, in the Q&A period that will follow the next two presentations. Right now, Lori, let's turn the tables on the audience and ask them a question.
Yes, the second poll for today, and coming up on your screen regarding IMU or INS products, what are the most common challenges your design integration team face? Again, we're asking for your top two selections here on this one. Among form factors, size and weight, power requirements, ease of integration, reliability, and support. All right, looks like we have 68% with form factor, 30% power requirements, 46% ease of integration, 47% reliability and support. Alan?
Well, clearly form factor is the winner here, with 2/3 of the audience voting for that. Again, we're asking you to select two, so it's hard to clearly pick a trend or a winner. But gentlemen, what do you say? How does this reflect or align with what you hear from your customers in the marketplace?
Yeah, thanks, Alan. This is David Hoy once again. The findings from our audience are consistent with what we hear from customers worldwide, where everyone's trying to achieve, as they discussed in the first poll, higher performance, lower noise in smaller, lighter weight sizes. And if the audience were to take a closer look at our product line from Mcor, you can see that in our QMEMS product technology, as Sergey demonstrated here, high-end performance in form factors, approximately the third the size of legacy ring laser gyros or fog units. In our closed loop fog line, you'll hear David talk about, our Orion series navigation systems that, deliver unrivaled performance in about a third of the size of older traditional legacy systems. So voice of customer is loud and clear. I think our product portfolio addresses many of the needs in today's applications. Thank you. Back to you, Alan.
Thanks, David. We'll look now at a couple of other applications: optical targeting, intelligence, surveillance, and reconnaissance, and underwater unmanned vehicles. Key parameters to these applications are high bandwidth and low angle random walk. An ideal solution for these would be fiber optic gyro technology. And to learn more about those, we're going to hear from David Blumenfeld, Director of Fiber Optic Gyroscope Research and Development at Emcore since 2020. Mr. Blumenfeld joined Emcore as the lead hardware designer in 2016 for the company's development of the Emcore Hawkeye series fog products, and served as the technical lead on the EN300 fog inertial measurement unit. He has more than 10 years of experience in low noise analog electronics design. He received his bachelor's in electrical engineering from the University of California, Los Angeles, and his master's from the University of Southern California. Prior to Emcore, he worked at the University of Southern California Information Sciences Institute, where his research focused on developing low-cost prototyping manufacturing for IC designers. David, let's hear more about fiber optic gyros.
Thanks, Alan, and thanks everyone for joining. So before I dive into the technical topics, just want to give a brief overview of what I'll be talking about today. I'll be talking about how Emcore's fiber optic technology enables us to deliver higher performance than our competitors for bandwidth, angle random walk, in-run bias instability, and bias over temperature. This makes our fog products a perfect fit for applications such as airborne optical targeting systems, ISR, aided autonomous navigation, and north keeping. I'll then discuss how our technology allows us to take a unique approach to building fogs, which means we can deliver superior performance in the same package size as our competition. Lastly, I'll look to the future and talk about a fog-based inertial navigation system that we are looking to offer later this year. Before talking about Emcore's fog technology, I'd like to give a brief overview of the legacy fog technology in the market today and the potential pitfalls in their design choices. Below is a block diagram of a typical fog-based inertial measurement unit that is offered by many of Emcore's competitors. The general principle of operation is the laser diode provides light that is split into three and runs clockwise and counterclockwise through a fiber optic coil. I refer to the coil here as x-axis gyro, y-axis gyro, and z-axis gyro. The light then comes back, is combined, and then is detected by the monitor diode. The phase shift between the clockwise and counterclockwise light is directly correlated to the induced rotation rate of the system. This is commonly referred to in textbooks as the Sagnac effect. There are a couple design choices in the legacy products that lead to poorer performance than Emcore's products. Because each of these blocks are discrete components, our competitors need to use a single light source to account for size constraints. This means that the system has a lot of splices. Splices are connecting two pieces of fiber together, and so at each of these blocks, you have a splice. Every time you have a splice, you have the opportunity for the polarization of the light to get distorted. And this has a direct impact on your bias performance, especially over temperature. Furthermore, having a lot of splices means there's a lot of attenuation in the system between the laser diode and the monitor diode. This leads to an overall degraded power efficiency, which means a poorer signal-to-noise ratio for the detected power on the monitor diode, which as a result will degrade your angle random walk performance. Now moving on to Mcor's technology. We have developed a transceiver that integrates most of the discrete components on the previous slide into a single package that is extremely compact. This transceiver design allows us to use 3 light sources instead of 1. Now, what does that do for gyro level performance? By having one transceiver and so many components integrated into a single package, we have significantly less splices than the competition, which means superior bias over temperature performance. We also have inserted a circulator in our transceiver before the monitor diode, as shown here. This circulator doubles the signal strength and leads to a superior angle random walk. We also have an in-house designed IOC that has been qualified for high-performance space-grade programs. Taking a 30,000-foot view, our transceiver and IOC are designed and manufactured in-house by our world-class foundry, which is a major differentiator for Mcor. This means we have higher quality control and can do rapid continuous improvement on the core technology used in our FOG products. Another technical edge Mcor has is its closed-loop gyroscope capability. This slide shows the same block diagram on the left that I showed on the previous slide. The detected optical power from the photodiode has a raised cosine dependence on the induced rotation rate, labeled here as delta phi r. If we then plot detected optical power as a function of induced rotation rate, you get a plot like the one here on the right. In an open loop system, the detected power can land anywhere on this curve. This means that you could have a situation like what I show here by this green dot, where you have very low detected rotation rate. If you find the detected rotation rate near 0 and are at this green point, you'll see that you have low sensitivity and low linearity. Emcore has developed a lithium niobate IOC with an optical phase modulator, which essentially modifies the index of refraction of the waveguide and hence modulates the phase of the light. In a closed-loop system, we use this phase modulator to induce a phase change equal and opposite to the induced rotation rate. This allows us to keep the detected light on the photodetector in the most sensitive and linear region of this curve, as shown by this purple dot here. What that means at the gyro level is you're able to get better scale factor linearity, dynamic range, and bias performance than equivalent open loop gyroscopes. So looking at some of the key performance parameters of the FOG, our world-class optics technology and closed-loop technology gives us superior performance in all of the key gyroscope performance parameters. As a side note, a key difference between our FOG products and our QMEMS products is gyroscope bandwidth. Typically, our FOG products have a bandwidth of greater than 1 kilohertz, whereas our QMEMS products have a bandwidth on the order of hundreds of hertz. This makes the FOG products a perfect fit for applications with a high level of dynamics, such as the examples I presented on previous slides. So now that I've talked about Mcor's underlying optics technology, I'd like to talk about a couple products that put it to use. The first is the EN300, which is an inertial measurement unit in the same package size and functionality as the Northrop Grumman LN200, but with superior performance. By using 3 independent light sources and our unique transceiver design, we can achieve 10x better angle random walk than the LN200. To show this in action, below is a root-Allen variance curve comparing the LN200 to the EN300, and this is based on actual data taken in a laboratory. As I'll talk about in subsequent slides, we have 3 performance grades for the EN300, the -1, the -3, and the -5. As you can see, the EN300 achieves a typical ARW of 0.007 degrees per root hour in comparison to 0.07 degrees per root hour for the LN200. I'll show some more detailed test data on subsequent slides outlining this performance improvement. So now just want to give a brief overview of the different performance grades for the EN300 and how they compare with the LN200. As I mentioned previously, we have 3 different performance grades, the -1, the -3, and the -5. And the key differences between them is gyro and accel bias over temperature and angle random walk. For the gyros, the EN300 beats the LN200 for all 3 performance grades, in some cases by as much as 20x. This plot here is the same root-Allen variance curve that I showed on a previous slide, but now just showing it as a function of time. We have here a comparison between the EN300-3 and the LN200, and this data was taken in a quiescent laboratory environment where both IMUs are outputting 3600 Hertz gyro data. The blue dots are the LN200 and the orange dots are the EN300. This is the x-axis gyro, this is the y-axis gyro, and this is the z-axis gyro. And as you can see on all 3, the EN300-3 has significantly less noise than the LN200. Taking a look at the same data I showed on the last slide, but now just showing it as a PSD, you can see that the EN300 has fundamentally lower noise floor than the LN200. And this is because of our transceiver architecture, our use of a circulator, which gives us better signal-to-noise ratio on the monitor diode, and hence lower ARW. We then took an EN300-5, which is our lowest performance grade EN300, and tested it over temperature, -40 to 71 C, and did the same for the LN200. We measured the gyroscope bias at a variety of different points between those 2 temperature extremes. The EN300 has significantly less gyro bias variation over temperature on all 3 axes in comparison to the LN200. Recently, we had an EN300-5 tested by a customer where they took an EN300-5 and an LN200. They put it in a gimbal system and did a basic gimbal alignment using a common filter over a 2-hour period. And as you can see, the EN300-5 beat the LN200 in alignment for all 3 gyroscopes, all 3 accelerometers, by a factor of 2 and in some cases as high as a factor of 10. Recently, we released the EN300-1 into full rate production, and this is a short-term navigation grade IMU with less than 0.1 degrees per hour bias over temperature performance. Below is a plot of the first 12 IMUs that were built in production of the EN300-1. And as you can see, we can consistently get below 0.1 degrees per hour gyro bias, and on average, we get about 0.05 degrees per hour gyro bias, which is a 20x performance improvement in comparison to the LN200. Taking one of the IMUs from the previous slide and showing a little bit more detail, this is an EN300-1, all 3 gyros bias over temperature. And as you can see, there's significantly less variation in our EN300-1, and we are able to achieve 20x better performance in terms of bias over temperature in comparison to the LN200. Now looking to the future, we're currently working on the Orion EN2000. This is a navigation grade inertial measurement unit that is also going to be offered as an inertial navigation system. Because we have this compact transceiver design, it enables us to build these what we refer to as pucks, where we're able to integrate the transceiver, IOC, and coil into a single package as shown here. And this enables us to build an IMU that is 1/3 of the size of competitors that are manufacturing IMUs and INSs in a similar performance category. And it also enables us to have a modular assembly process, which means we can build these IMUs at a very large scale. We recently had a prototype tested, first over temperature, -40 degrees to 71 C, to extract bias over temperature performance. And then we tested it at room temperature in a quiescent environment to get a root-Allen variance curve. Below is data for one of the gyros in that prototype. On the left, the blue data is the gyro bias over temperature, and the red curve is a temperature sensor inside the gyro. And as you can see, we have significantly low variation over temperature with a 1 sigma of 0.012 degrees per hour. On the right here is our root-Allen variance curve, where we demonstrated an angle random walk of 0.0013 degrees per root hour and in-run instability of 0.0025 degrees per hour. We're currently working on refining our manufacturing process and our assembly and test in order to get our bias to 0.007 degrees per hour and our angle random walk to 0.0008 degrees per root hour. And we're confident that we are going to get there in order to release this product into full rate production before the end of the year. So in summary, Mcor's unique transceiver design enables us to build compact fiber optic gyroscopes with minimal splices, better power efficiency, which means better angle random walk and bias stability. Our lithium niobate technology enables us to build a closed loop fiber optic gyroscope, which means better scale factor linearity, dynamic range, and bias stability than equivalent open loop gyroscopes. Our world-class foundry enables continuous improvement of the transceiver and IOC design so that we can develop next-generation technology at a much more rapid pace than our competitors. And then I talked about our two flagship IMU and INS products, the EN300, which is a short-term navigation grade IMU that is a true form-fit function replacement for the tactical grade LN200, and the Orion EN2000, which is a navigation grade IMU at a third of the size as its competitors. Back to you, Alan.
Thanks, David. We're going to hear next from David Hoy, Director of Navigation, Sales, and Marketing, to tie all of this technology together into practical information in the field for all of you out there. David is the Director of Navigation and Sales and Marketing, as I said, for Emcore. He currently leads revenue generation, customer development, and new business pursuits, Marcom, and sales management. He received his business and marketing degrees from Western Michigan University in 1986 and has more than 30 years of experience in strategic planning, operations management, new business development, brand management, product development, national account and field sales, sales management, and commercial excellence in several different industry segments. David, your presentation, please.
Yes, thanks, Alan, and thank you everyone for joining. Let's take a close look at our newer product solutions for 2021. External customers and independent test houses are acknowledging our world-class leading technical performance. In a study completed earlier this year, the SDI 500 IMU ranked #1 out of 19 competitive IMUs for compelling performance, cost, SWaP, and maturity. The study used a Monte Carlo simulation method to compare the 19 IMUs. A short and long munitions trajectory was evaluated. The CEP, or circular error probable position error, of the SDI 500 was 25% better than the HG 1700 in short trajectory and over 80% better than the HG 1700 in the long trajectory evaluation. This summer, Mcor will release a RevF block upgrade to its popular SDI 500 The Rev-F incorporates design, manufacturing, process updates to enhance overall IMU performance, improve manufacturing yields, production efficiency, and lower cost. This Rev-F IMU maintains the current 1 degree per hour gyro and 1 millig Excel bias over temperature, plus the IMU will incorporate new features such as a higher rate 70G linear accelerometer. The SDI 500 production ATP statistics show a 0.5 degree per hour mean gyro bias over temperature across all IMUs that we ship today. We do produce a number of gyros with performance ranges from 3 to 20 degrees per hour. We are introducing those commercial gyros and accels into a no license required IMU for lower dynamic environment applications. Plus or minus 490 degrees per second dynamic range, plus or minus 20G calibrated linear accelerometer range, and over a minus 40 to plus 71 C operating temperature range. This SDC commercial IMU is available in 4 different performance grades and is ideal for a variety of civil, industrial, and marine applications, ranging from 1 degree per hour 3 millig Excel all the way up to 20 degree per hour gyro 5 millig Excel bias. We are accepting orders for this commercial IMU now for shipment starting in August. The EN300, as David mentioned earlier, is a higher performing form, fit, functional upgrade replacement to the legacy LN200 with demonstrated gyro performance 2 to 20 times better than the LN200, and it's ITAR free. With 0.2 degrees per hour gyro, 300 micro G Excel bias in our base model, and extremely low 0.04 degree per hour in-run gyro bias stability, the EN300 is ideal for a variety of mission-critical navigation applications. Another new tactical IMU from Mcor is our SDI 170. The SDI 170 is a higher performing form, fit, functional replacement upgrade to the legacy HG1700 ring laser gyro, IMU. Refer to the Allen deviation graph in the lower corner, which demonstrates the SDI 170's superior performance advantage over the HG1700. This IMU repackages the same mature, reliable, industry-leading proven performance in the SDI 500 using its internal assembly, DSP, and interface board into a backwards compatible HG1700 form factor, including height, weight, mounting locations, connector pins, power supply, standard RS422 HG1700 synchronous SDLC output data messages. The SDI 170 is ideal for continuous use applications with higher MTBF mean time between failure rating than the HG1700. It too is non-ITAR rated for export purposes, and we are shipping LRIP units today to customers around the world. Earlier in 2021, we placed SDI 170 T&E units with different customers. A leading international scientific and technology research council, Defense Industries Research and Development Institute, concluded the SDI 170 IMU meets all of its published specifications, is mechanically and electronically backwards compatible to the HG1700, and that its measured gyro and accelerometer performances correlate to Mcor's ATP data. Their conclusions reflect the SDI 170 is a low-risk option to replacing or upgrading legacy HG1700 applications today. In addition to the high-performing EN300, Mcor is introducing its top-of-the-line Orion series of navigation systems. The EN1000 or EN2000 fog-based navigation grade system provides excellent 0.015 down to as little as 0.007 degrees per hour gyro bias over temperature, and even greater or higher performing 0.003 degrees per hour bias in-run stability over a dynamic range of 600 degrees per second and 60 G linear accelerometer range. But what really sets the Orion navigation systems apart from other competing systems is its compact size at only 125 cubic inches and extremely low weight of 7.5 pounds, and its low power, making it ideal for many smaller, lighter, autonomous applications that are being developed today. We are accepting test and evaluation orders for this Orion Series IMU now for shipments later this year. In addition to IMUs and INF solutions, Mcor offers precision quartz MEMS and closed-loop fog single-axis gyros. Our low-noise, tactical 1 degree per hour QMEMS gyros, like the SDD 3000, are ideal for targeting, stabilization, and flight control applications. Our 0.002 degrees per root hour low-noise navigation-grade fogs, like the EG1300, are ideal for non-line of sight and north-finding applications. These two products are available today and are shipping to customers worldwide. In summary, thanks for spending your time with us today. And in summary, the advantages of doing business with Mcor are unique tactical to navigation-grade high-performance sensor offerings, extending industry-leading quartz MEMS performance to navigation-grade, closed-loop fog technology that outperforms the competition by a factor of 20x, and new IMU and INS product offerings with SWaP-C advantages over legacy alternatives, unmatched performance for price. And with that, back to you, Alan.
Thanks very much, David. While the audience takes a look at these further resources, I urge you to send more questions in. We have several from the audience so far. I have a question for you now, the audience, and Lori, let's roll that one.
Yes, poll number 3 for today. Which best describes your GNSS plus inertial application? And in this case, we're having you select just one: highly dynamic and high accuracy, highly dynamic and low accuracy, low dynamic and high accuracy, low dynamic and low accuracy. All right, it looks like we've got our responses there. Alan?
Well, Lori, just as an aside, this reminds me of Stephen Covey's 4 quadrants: high urgency and importance, high and low. But to refer this to inertial technology, I'm going to kick it over to the panel and ask them to talk about, in particular, which are the high dynamic and high accuracy applications and which are the low dynamic and high accuracy applications that our audience seems to be most interested in. Gentlemen?
Hey, Alan, this is David here once again. And regardless of dynamic range, high accuracy, high accuracy, high accuracy seems to be the theme here, or at least 2 times. And with that, at least from Mcor, you know, we have our focus on inertial solutions for the market segments we serve starts with a baseline tactical grade performance all the way on up to high-end navigation performance. So if you look at our product lines once again, whether it's in our quartz MEMS or our closed loop fog, I think that the audience will find that we have several product solutions that are ideally suited for a wide range of applications, whether it's autonomous navigation, either on a lower dynamic land vehicle or a fixed wing UAV, all the way into high dynamic applications, whether it's an aerial target and or a weapon system.
Thanks, David. And indeed, we wouldn't be here very much, at least if we were interested in low accuracy. Of course, everyone wants to know about high accuracy. Some questions for our panel. First of all, for David Blumenfeld, panelist needs, an attendee needs a gyro with the best in-run angle random walk. What is the performance of your device?
That's a great question. So I talked a little bit about the EN2000 at the end. That's our highest performing IMU from an angle random walk standpoint. We'll be offering it later this year with angle random walk of 0.0008 degrees per root hour. And on the single axis rate sensor side, we have the EG1300, which is currently in full-scale production, which offers an ARW of 0.002 degrees per root hour. And we do have other gyroscope and IMU products that are lower grade than that. Our EG120, which is the lowest grade gyroscope that we offer, has an angle random walk of 0.4 degrees per root hour. So we offer a very wide variety of ARW performance.
Thank you, David. Sergey, a question for you. If quartz gyro turn on bias is about 0.5 degrees per hour, how can you achieve gyro compassing accuracy of 1 degree without carouseling?
Thank you for the question. So there is no way to achieve 1 degree without cruising with gyroscope turn on 0.5 degree per hour. For our latitude, 0.1 degree per hour provide about 2.5, maybe 3 degree accuracy before cruising. But we demonstrated high-end tactical grade, and our performance it's about 0.1 degree per hour. If you have gyroscope with 0.1 degree per hour from run and over temperature, you're able to demonstrate accuracy better than 1 degree per hour before cruising.
Thank you, Sergey. David Hoy, question for you. I am currently using an HG1700 and would like a replacement. Do you have one?
Oh boy, don't I, Alan. Yes, we do. Our SDI 170, as discussed earlier, is a form-fit functional performance upgrade to the HG 1700. Both internal and external testing of the IMU proves equal to or better performance over the rugged environmental conditions. We are taking orders for those units today and with shipments beginning as early as September in full rate production. Back to you, Alan.
Thanks. Another question for Sergey. If silicon is higher proof mass for the gyros, does this mean that the driving fork frequency is lower than silicon? Is there a common frequency range?
Actually, it's not. Could you please navigate me to my slide, size and amplitude matters? Yes, like we're talking about, we increase proof mass because we age deeper. When you age deeper, your proof mass proportional to how deep you age, and thickness of your beam proportional to the how deep you age, and stiffness of this beam proportional to the depth of aging, as well as proof mass. Frequency is square root of proof mass divided by stiffness, and actually frequency it's not depends of how deep do you age. So if you increase proof mass, your frequency remains the same because your stiffness increases. What about conventional frequency? Actually, it really depends on application and what's your vibration frequencies when you use this gyroscope. but you couldn't, your operational frequency for gyroscope couldn't be lower than about 6 kilohertz, and it could be up to tens of kilohertz, and maybe sometimes hundreds of kilohertz. Again, it really depends on the application.
Thank you, Sergey. David Hoy, we've got a raft of questions for you, and then one more for Sergey. First one for you, David. Lead times for an LN200 are too long. Do you have a replacement for that?
Once again, Alan, affirmative. Yes, we do. Our EN300 closed-loop fog, as discussed in this presentation, is a form-fit, functional performance upgrade to the LN200 with up to 20 times better performance. And today is available for shipment to our customers in lead times less than 4 weeks from receipt of the order. Back to you, Alan.
And don't go away, David, because here's a question. Will the current SDI 500 chassis become obsolete? What is the production time frame for the new smaller SDI 500? And will you continue to support the current grading and binning scheme A, B, or C?
Thanks for the question. First of all, I'll take it in stages. Will the current SDI 500 chassis become obsolete? We will continue to maintain the current SDI 500 for legacy platforms or customers that require that size and fit, and don't want to undertake any significant requal efforts. Over time, if you can, in theory, over time, if you can get the same performance in a smaller, lighter weight, lower power, possibly cheaper IMU, naturally the SDI 500 may become obsolete. But we're going to let customers decide on that. And looking at production lead time for the smaller IMU, we're on a path right now to introduce the, we'll call it smaller IMU in LRIP quantities in late 2022 to early 2023. And we will continue to support what we'll call the binning or grading, being A, B, or C, and possibly introduce derivative performance classes, as well as dynamic ranges and temperature ranges from the IMU to serve both commercial, marine, industrial, and military applications.
Thanks, David.
You're welcome.
Yeah. Another question for Sergey. Turning our vision to space now, where an increasing number of GNSS and INS applications are being put into use. Sergey, what would you say is the minimum size limit for Quartz MEMS products? And could they be suitable for microsats or CubeSats, for example?
Oh, yes. Could you please navigate to my supplementary slide nugget overview? So right now we have a number of nuggets, and today I discuss you in the very large, we call it nugget, like actually it's our gyroscope, very large gyroscope fork. But we have medium size and we have small size. And after that we have some for industrial publication, even slightly smaller. Right now I am not ready to answer what's the smallest size. It depends of your performance. Like small, it's your performance degrade. But if you look on this size, and if you see that one of this size is suitable for your application, we can build your gyroscope and on this size and provide to you. And question, could it be suitable for microsats? We have to discuss, because we have to know parameters, like first of all, what's your total size, and is it possible to fit here? What is your requirement performance, and can we satisfy your performance with this size? We have to see all requirements, and maybe we can discuss offline, and we will provide you answers.
Thank you, Sergey. David Blumenfeld, one here for you. One of our attendees has been a faithful webinar audience member because they have heard about the photonic integrated chip, the PIC inside. Does Mcor have a photonic integrated chip?
Yeah, so we have what we call an IOC, which is a lithium niobate integrated optic chip. And there's a few similarities to the PIC and a few key differences. So the PIC has passive optical components like splitters and combiners, but it does not have any active electro-optical elements. And that means that the PIC does not have the ability to actively change the phase of the light, and hence cannot operate a gyro as a closed loop. In comparison, our IOC, due to the properties of lithium niobate, is able to actively change the index of refraction of our waveguide, which means that we can actively control the phase of the light going through the chip. And so as a result of that, the PIC-based gyro is really an open loop gyro, whereas an IOC-based gyro is a closed loop gyro. And with a closed loop gyro, like I talked about a little bit in my slides, you get better scale factor linearity, bias stability, and dynamic range in comparison to open loop gyros.
Thanks, David. David Hoy, two more questions from you and then we'll close it out. First one, audience member needs an IMU and is located in a country that perhaps is not on the let us say the normal distribution network. Can you ship products to me?
Thanks for the question. Let me start by saying if the caller, the attendee is in what we'll call a NATO-friendly and or green country, we have several options available for shipment, starting with soon to be our newly announced commercial IMU that is predicated on the Quart MEMS technology. That product will be able to ship to any NATO-friendly green country in the world without licensing or end-use certificate. For other IMUs, such as the SDI 500, our EN 300, and even our higher-end Orion series EN 1000, those are non-ITAR IMUs, but fall under the control of U.S. Commerce. They will require a simple commerce license prior to shipment, which is traditionally easy to obtain in as little as 4 to 6 weeks' time. And I hope that answers the caller's question.
Thank you, David. And thank you to the audience for attending this webinar on inertial sensor SWaP for tactical and navigation grade. You'll receive, as Lori will soon tell you, you'll receive a copy of this webinar in your email, and we encourage you to share it with your colleagues and anyone else interested in the content. Thanks again to all of our panelists, and I'd like to give you each the opportunity to share some closing words with the audience, starting with Sergey.
Thank you. Thank you very much for participating in this webinar. Really appreciate your time. I appreciate your questions. I hope everything will be useful. You learn some new information about our current product as well as our short future and long future products. And we are open to discuss and answer all your questions after this webinar. Please contact to us. And yeah, thank you very much.
Thank you, Sergey. David Blumenfeld, closing words from you.
Sure. Yeah. Thank you everyone for joining and taking time out of your busy schedules. We've been working tirelessly nights and weekends on the R&D team developing our FOG product line, We're really excited for it to start getting into customers' hands, seeing their product applications come to life. So really appreciate it. And like Sergey said, you know, our technical team is always looking and excited to talk to customers about their applications and you know, any questions that they have. So don't be a stranger and feel free to reach out.
Right. And David Hoy, over to you.
Thank you. Yeah, thank you everyone for attending today. These are exciting times at Emcore. We have, as we demonstrated, a wide variety of products and technology ideally suited for a variety of applications around the world. And as markets are beginning to open up as we are exiting these COVID times, hopefully today we've demonstrated, going back to the survey questions here, customers are looking for low gyro noise. They're looking for solutions that have low in-run bias in smaller sizes, lower weight, lower power. Hopefully you will have seen that both in our QMEMS and FOG product technologies options for your applications in various autonomous navigation solutions that require precision without aiding or precision during degraded filtering GPS, GNSS environments, as well as our low noise solutions for non-light of sight targeting and optical intelligence systems. So with that, we thank you. My point of contact details, as well as Andrew Pop, our Senior Director of Marketing, are enclosed in this presentation, and we welcome your engagement. Thank you again.
Thanks, David, and just like to echo your sentiments. We welcome your engagement. It's been a pleasure talking with you on this webinar, and we look forward to your participation and attendance in further webinars. We have one just about every month, and just be alert to your email feed for news of that. Thanks again to Emcore for making it possible for us to present this in-depth technical information. Thank you once again.
All right. And most importantly, again, thank you for joining us. This is Lori Dearman saying, hope we see you on the next one. Bye for now.